In this video, we're going to continue learning about compression, and I'm going to teach you how to build Huffman encoded message in the Java programming language. So we will continue with the public API methods compress and decompress, and this time we will use the Huffman encoding algorithm to compress our message, and we'll see that it's an optimal encoding for lossless compression. So let's jump right into it here. I'm going to go ahead and say create a new Java project, and let's go and call it Huffman Encoder. And let's create a new Java class called Huffman Encoder. And I'm going to break this down step by step. So let's start with our two public API methods that we're going to introduce. And they are going to be encode and or compress, if you and decompress. Okay, so let's say public, and we know we're going to return something. I'm just going to say that it's a Huffman encoded result. You'll see why that is in a bit. We're going to say compress, and we're going to take a string of data. Okay, let's just return null right away, and we'll return a static class Huffman encoded result, just to get rid of our compiler error right away. So there's our compress method, and we're also going to have a decompress method, public string decompress final Huffman, given a Huffman encoded result. We're going to go ahead and decompress that. Okay, and again we're going to just say return null. Okay, so here's the skeleton of our program. We're going to try to do this in about 200 lines of code or less, and I've seen a lot of tutorials on YouTube about Huffman encoding. I'm going to try to make this the definitive the definitive tutorial on this. So 200 lines of code and pretty step-by-step approach. So let's start here. The first thing that we want to do is we want to count the frequency of each of the characters in each of the unique characters in our string. Okay, so we're going to say final int. We're just going to use an integer array to maintain the frequencies. Freq is equal to new int array, and we have to know how many characters are supported in our alphabet in terms of whatever we're encoding. I'm going to assume ASCII, and so in ASCII there's 256 characters, I believe, that are supported for printable characters. So let's say private static final int, and let's just call it alphabet size is equal to 256. Okay, and we're just going to declare, and note, you know, the particular string we're looking at might not have all of these alphabet characters used. That's okay, but we should at least support any of those characters. So we're going to come in here and we're going to loop through final car character in our data to char array. So we're going to go through each one of the characters inside of our string of data, and what we're going to say is that the frequency of that character, remember a character can be treated like an integer, that offset is going to basically get incremented, and we're going to return that frequency array. Okay? So now we're just going to say return freq. So actually we need to break this out into a method. So let's say private static int build frequency table final string data, and we're going to basically copy all of this code in here and paste it in there. So that's step one, right? And so if we were to, let's continue to return null from here. So if we were to very quickly come and build a main method, public static void main string args, and we were to say that final string test is equal to ABC, DEFG, and let's put two F's in there, and we were going to say final int array frequency table is equal to build frequency table on test, and system.out.println ft. Let's run this program really quickly. Oh, oops, yeah, that's not going to do it. We have to, we'd have to actually print out the contents of the array. Let's just set a breakpoint here and run this in the debugger. So now here we can see the array, and let's see if we can find one with. So if we knew what the, like 97 I think is A, so look, there you go, 97, 1, 98, 99. If we keep going, there's 2, that's going to be mapping to F, right? So you can see that we've incremented the character as an integer for each of these indices, okay? So I think that's fairly straightforward, right? So we can, that's step number one. Step number one in this algorithm is just to say final int frequency table is equal to build frequency table on our data. Now that that's done, the next thing that we want to do is that we want to build a data structure called a Huffman tree, okay? And if you're not familiar with this, I would encourage you to look this up online. So here we can come in here. So here on my screen I brought up the Wikipedia entry for Huffman coding, and I want you to focus on this diagram labeled constructing a Huffman tree. So here we can see step by step how the tree is constructed. We start with the following characters here in some particular Huffman string, and we start by identifying all the unique characters and their frequencies. That's what we've done. Then what we do is we merge nodes, and we do it based on starting with the smallest frequency. So here you can see that node D and node E in the second step were merged into this subtree here, and 11 represents the sum of their frequencies, right? So 6 plus 5 is 11, so that's why we built this tree. Next we're going to continue, and we're going to say the next two the next two least frequently occurring items are C and D, or excuse me, C and B, right? With frequencies of 6 and 7 respectively. And so here we can we merge them down here in this next step, right? So now we have items 15, 13, and 11, and we're going to merge those. These are the two smallest items. So we merge 13 and 11, and we produce 24 and 15. And finally, we're left with 15 and 24. We merge those, we get 39. So here's the tree that we ultimately want to, this sorted binary tree that we ultimately want to construct. And I would say intellectually this is the hardest part of the challenge. It's not that hard of a challenge to begin with, but wrapping your mind around this is the hardest part. And I think if you, we're going to use a couple of tools. We're going to use a priority queue to help us build this tree, and it should be fairly straightforward. So let's go ahead and start doing that. All right. So so let's go ahead and write a method here called private static node we'll see what this is in a minute. Build Huffman Tree. The node is going to be the root of the tree. Int array, and we need the frequency table in order to build the tree. So let's go ahead and introduce this class here, static class node. Okay, and really let's talk about what a node is, right? A node is going to have final character. There's going to be a character associated with a node, and as we saw in that diagram, and there's going to be private final int frequency. The node's going to have a frequency associated with it. Oops, character. Private final node left child and private final node right child. Okay, so we've got those private member fields, private node, and we're going to construct this thing, so bear with me. Here, final and frequency, final node left child, final node right child. Okay, so this dot character, this dot frequency is equal to frequency, this dot left node, left child is equal to left, this dot right is equal to right. Okay, so that's fairly straightforward. And what we're going to have on here is a nice convenience method that says Boolean is leaf. So if you don't have any left or right children, we're going to call you a leaf. So return left, this dot left child is null, and this dot right child is equal to null. Okay, that's fairly straightforward. And we're going to want a way of, we're going to want to make these things comparable based on their frequency. So I'm going to say that this implements comparable of node. And just like in run length encoding, this thing's going to complain. We're going to implement the method. We're going to have a compare to method. And this compare to method is going to be fairly straightforward. What we're going to say is that in frequency comparison is equal to, and we're just going to say integer dot compare this dot character frequency, this dot frequency, and that dot, or O dot frequency, right? O being the other node. Actually, I like calling it that. That dot frequency, and if they're not equal, if frequency comparison is not equal to 0, means they're not equal, return frequency comparison. Otherwise, we're going to, just for consistency, we're going to compare based on the character, and this is not really effective. This doesn't affect the quality of the algorithm, but it will mean that the tree that we build is always this always the same. It's deterministic. Okay, so fairly simple comparison way to compare nodes, right? And yeah, so now that we have a node, we're going to go back and we are going to build the Huffman tree for that node. So let's go ahead and start that. So here, and where did what was my compress method? Here we are. So here we go. So we're going to say final. This is the key data structure that we're going to use to build this tree. We're going to use a priority queue. If you don't know what that is, I encourage you to go and look it up. I'm not going to talk about that in this video, but here we go. Let's just summarize what's going to happen. So we have our priority queue, and we're going to say for character I equals 0, I less than alphabet size I plus plus. So we'll go through all possible characters in our alphabet, and we're going to say if the frequency, the array that we passed in, of that character is greater than 0, that means it's occurred in our encoded message, then we're going to say priority queue dot add. We're going to create a new node. We're going to say I, that's the character, its frequency is character of I, and it's got no children. Okay, so we're basically going to make a new leaf node for that character, and how we're going to record how many times what its frequency is in the node, and we're saying here it's got no left or right children. So now after this process finishes, we should have a bunch of nodes flattened out in a priority queue, and when we invoke poll, we should get a value back from the priority queue in the order of the basically the frequency, the size of the frequency. So we'll see that in a minute here. So what we're going to say is while priority queue size is greater than 1. Now, yes, I haven't talked about what happens when the size of the queue is 1 exactly. I'll get to that in a minute. But let's say you had several of these nodes. While the size is 1, we're going to say greater than 1. Excuse me. We're going to say get the left node pq.poll priority queue.poll final node right is equal to priority queue.poll. So we're just going to get the next two leaf nodes from the priority queue, and we're going to merge them together. So we'll say final node parent is equal to new node, and we're going to give it a special character that indicates it's not a leaf node. I'm going to use the null character. So the null character indicates that this is not a leaf node. And left, and we're going to say what is left's frequency. We're going to add that to right's frequency. Right, that's going to be the frequency of this node. Right, and we're going to say that in this parent node that we're merging, the left child is simply left and the right child is right. Okay, so we've taken these two elements out of the priority queue, merge them together into this parent node, and we're going to keep going through the priority queue and until we reach one node, which would be the root of the tree. Okay, and after we're just going to say priority queue dot add in the loop the parent, right? Pretty slick. And we're going to simply return the priority queue dot poll, which will give us the root node, and that root node will be connected to all of the others, right? So that's how we're going to return this root of the tree. And there's only one step that remains, which is if the size, let's say you only had a message with one character in it, if the size of the priority queue is equal to 1 and 1, then this little technique I've highlighted here won't work. So we just have to say priority queue dot add new node, and we'll continue to use the null character, and we will say that it's just 1. Its frequency should be 1 and only 1, right? And null, right? So we just convert that particular element into a non-leaf node. Okay, so you can choose how you want to deal with this particular case. So this is not the focus of the method. The focus of the method is here, what happens in the while loop, really, and up here in the for loop. So now we've constructed this tree, right? So let's see what happens when we invoke. So let's say after we do this, we want to see what this root node looks like, just like we did in the debugger there. So let's say final node root is equal to build Huffman Tree, and we're going to give it the frequency table, right? And in our test here at the bottom in the main method, let's say final node n is equal to build Huffman Tree on ft, and we can just print n. And let's set the breakpoint right here again. So actually, it's a little, I want to walk the step through that code, so let's set the breakpoint up there. So, oops. So here I want to step in, not step over. So now we're in this method, right? And we're going to walk through it. We build the priority queue. Let's speed through that. So now we have our priority queue has 7 items in it, right? And they're all flattened out. All of them have no left or right children. Just all of the flat tokens in our message, right? And the frequency of that token. We should see, I think we said F. Yeah, it has a frequency of 2. So we're going to skip over this special case where the priority queue size is 1. We're going to come down here, and while we're going to pick off the left and right, and we're going to see A has a frequency of 1, B has a frequency of 1. We could have picked off any other item that had a frequency of 1 for the priority queue. Okay, but that's if our compare to method didn't take the character into account. That's why we use that second comparison in the compare to method. So now you can see here deterministically every time you run this program we'll pick off A and B first, and now we're going to merge those into a new node called parent. So if we look at parent, we'll see that its frequency is 2, and its left child is A, and its right child is B. And we're going to rinse and repeat this process until the very end, where we have our tree. And once we step out, we should be able to see this is our tree. And you can examine this tree if you want, but it's a binary tree here. It's got, it tells you what the total frequency is, 8. 1, 2, 3, 4, 5, 6, 7, 8. That's correct. And yeah, you can walk through this tree and see what it looks like. This is the key part of the data structure. This is the key data structure that's used for this algorithm. So now you have the frequency table built, and you also have the root of the Huffman tree available to you. Okay, there's really only one more. Well, there's 2 more steps involved here. So this next method I'm going to build, let's call it private static. It's going to be a map of character to string. We're going to give it the not so helpful name of build lookup table. You'll see what this does in a second, and it's going to take the node. It's going to take the node which is the root node of the Huffman tree, and let's return null for a second. What it's basically this method is going to do is that we are going to map each character to a binary encoding, and the length of the binary encoding for each character is going to depend on how frequently that character occurs. So the more a particular character occurs in our data set, in our message, in our string message, then the shorter its binary encoding is going to be. Okay, so let's walk through this. It's going to be a recursive algorithm that we're going to use to build this, and after we might be a little confusing to look at the code, but once we see what the lookup table looks like, it should be very obvious what's going on. So that's, let's say, final map of character to string lookup table is equal to new hash map, right? And we're just going to call a method, a helper method here, that's going to call itself recursively, build lookup table impl, and we're going to pass in the root node, an empty string, and the lookup table. And we're just going to say, that's going to populate the lookup table, and we're going to say return lookup table. So this method doesn't exist, obviously. We have to create that method, and yeah, so let's come here. Okay. So all this method's going to say is if the node that we're looking at, let's call it node here in this method because it's going to call itself recursively. If the node is not a leaf, then call yourself on the left child with the string concatenated with a O. Every time we walk down the left child, by convention we're going to append an O, and this requires a little bit of theory understanding that you're going to have to pick up from the Wikipedia article, but anytime we sort of traverse down the left side of our binary tree, we're going to encode an O, and anytime we go down the right side of the binary tree, we're going to encode a 1. And that could be the opposite, but it's just a convention that we're going to use. So node.rightChild s plus 1, and we also need to give it the lookup table. So that's what the method takes. So that's what we're going to do. We're going to pass this in to do the conversion, and if it is a leaf node, we're simply going to say lookup table dot put for that particular node's character s. Okay. So now that we've done this, let's clean up our code a little bit, and so now we have just this step right here to add into our method. So we're going to say final map of character to string lookup table is equal to build the lookup table, and we're going to give it the root of the tree to build that from. And we're almost done here or there with the compression portion of this exercise. So if we were to say final map of character to string lookup is equal to build lookup table on n, let's see what that would look like. Step over, and I won't step in the implementation. Let's first step over it so you can see what the map looks like. So you have your lookup, and you can see here that at the root, C maps to 1, 1, 1. And actually, I don't think that's right. Hold on. Alright, so I found the bug I was looking for. Notice here I say build lookup table impl on left child and left child again. This should be right child. Okay, so if we were to run this again in the debugger, after we build the tree, come in here. If we build the lookup table, let's see what lookup looks like. Now it looks better. Now you see we have for each one of the characters in each one of the unique characters in our alphabet, we have a binary encoding. And notice that our input has two F's in it, and notice that F, the binary for F, is more efficiently encoded than the other characters. Each of the other characters uses sort of 3 binary digits, whereas F, which occurs more frequently in our text, only uses 2 binary digits. So that's where the savings come from in this tree. Okay, so now that we've done this, we just need to wrap it up and put a bow on the encoding aspect of this whole part of the exercise. So we're just going to say that we built the lookup table, and we're going to say return new Huffman encoded result, and we're going to give it the generated encoded data, the lookup table, and we're going to need a method here. We're going to write a method called generate encoded data. We're going to give it the data and the lookup table, and this is going to be a really simple method, and the root of the tree. So let's create that method. Okay. So given the data and the lookup table, how is it that we want to do this? Well, really simple. All we're going to say is final string builder is equal to new string builder, and we're going to say for final char character in data.toChar builder.append lookup table.get. We're going to get the character, and we're just basically going to get that binary string for that particular character and say return builder.toString. That's all we're going to do. And this method's going to return, of course, a string. And let's say that it's static. And I think, what is this complaining about? Oh, right. I think we need to update the constructor for the Huffman encoded result class that we introduced here in order to reflect that. So let's say Huffman encoded result, and it's going to take in a final string encoded data, encoded in binary of course, and final node root. It's just basically a tuple object here, final node root and final string encoded data. This is really just convenience for the sake of the tutorial. It's not necessary. This dot encoded data is equal to this dot root is equal to root. Okay, so now this covers the compression portion of this exercise. So in the next video, I will walk us through how to decompress data that's been encoded using this approach. And so far you can see we've kept our promise. The code base is only about 130 some odd lines of code, and that includes our main method. So please do like and subscribe to the videos. In our next video we will cover the topic of decompressing this binary encoded message. Thank you.